Today's background is a little town called Yaga that's only about an hour and maybe an hour and a half outside of Tokyo, and there's a really nice day walk that runs from the next town on the line called Yamakita up into the mountains where you can see a view of Mount Fuji and then back down into this nice little town of Yaga, which is basically just entirely a rice farming community. It's a really nice place to go. And this is probably a better suggestion back at the start of ISO when people were locked in houses rather than now when they're getting to get out. But if you're looking for something to read that's not physics, I can highly recommend this book by Ian Maloney. That's funny even if you haven't lived in Japan. It kind of has interesting experiences of being, I guess, a foreigner in a separate country, and sort of the interesting ways that culture interacts in those sorts of environments, being nice about it rather than what we're seeing in some countries at the moment. Okay, so today's lecture is on simple harmonic oscillators. It's a topic I know you've all covered pretty extensively in your first year classes, but I basically want to go back, make sure we're all on the same page, introduce a couple of new concepts, and set things up for the next two lectures where we're going to introduce systems that are oscillatory that lose energy, and systems that are oscillatory that we put energy into, and that's going to be a lot of new material that's actually quite interesting. So let's kick into it. So this section of the course I affectionately call Things on Springs. It's really hard to avoid a mechanics course without oscillations in there somewhere. The intent is to go a lot deeper than we do in first year. So the one big new concept I want to introduce today is a thing called velocity phase space. After the last lecture, you'll notice that we have, as a general rule, a thing that we call a Lagrangian that is a function of a set of positional variables, qi, a set of sort of momentum variables, q dot, and time. And this means that there's all the ways we normally think about drawing dynamics in mechanics that you learn in first year, like plotting position versus time, velocity versus time, everything versus time. And there's also a lot to be learned by plotting non-time parameters against each other. And one of the really common ones is to plot a qi dot versus a qi. In other words, velocities versus positions. And these are things that we call velocity phase spaces. They turn up quite a lot in physics, and I'm going to use a fairly simple system to explore it. It's sort of our familiar pendulum mass hanging from the rod. So let's go in and introduce this thing properly. We have a fixed point, and we'll do the rod case here so that we don't have to worry about tensions in strings and floppiness and so forth. And we have some body down here. The length of this rod connected to the body is A, the mass is M, the displacement angle here is theta, and we'll, just for sake of argument, consider the positive displacement direction to be in the anti-clockwise direction, just in case we want to be specific about any arguments here. And as you know, this executes a small segment of what would be rotational motion. So there's a position down here, which is the minimum, and that is, if we consider our fixed point up here, some distance down, mga, and then to get the height relative to that so that we can get our potential, as you know, we need to do a little bit of trigonometry, so we can just sort of blow up on this position down here. What we've got is, and I'll draw it in a very exaggerated fashion, it would be our mass down here at 0. When we rotate, our mass would be up here. This would be our angle theta in here. And then this distance here is A cos theta. And so we would write our potential energy term in this particular case if we wanted to, and this is what you'll see in a lot of the books, would be mga, which is the position here at the bottom, and then we're interested in the height above that, so it would be minus mga cos theta. So we're basically looking at our height just here being the difference between this height just here and this height just here, okay? Now, you can cluster the terms here and you just get mga 1 minus cos theta. Now, one thing you know about gravitational potential energy is you can set your zero pretty much to any height you want and it doesn't matter very much. So what we could do is assume that our zero position here is actually the height of the bob at the equilibrium position, and then we could write a different expression here for our potential energy. It would be minus mga cos theta. Okay, so what we'll be doing is calling this position here 0, and then just turning our height up, and our height is going to be given by that expression there. There's another way to see this, which is that the Lagrangian has terms in it, and we never actually use the Lagrangian itself. Whenever we deal with the Euler-Lagrange equation, we're always dealing with derivatives of the Lagrangian, whether it's with respect to x or x dot or whatever, right? And so terms that are constant in the key variables, x and sort of x and x dot, and time, the variables that are independent of that, will always disappear when we take those derivatives, okay? So you can imagine that this mga term here, m times g times a, is fixed. If it appears in the Lagrangian, whenever we take the derivative in that Lagrangian, that term disappears, so we don't really care about it. So you can kind of see this as two ways of getting rid of this term. One is just that height is sort of gauge invariant in gravitational systems. The other is just that there's you can see a constant term there that doesn't matter as far as the Lagrangian. You can make this disappear. And the second one is a theme that we'll come back to again and again as we go through these sorts of problems of identifying terms that we know don't matter, so we just don't even worry about them when it comes to the mathematics, okay? Anyway, we'll take this as our potential energy term for our pendulum. And then the other thing that we're going to need to consider in here is the kinetic energy, right? And it is T equals a half mv squared, as you know, always. And of course, our pendulum here is executing essentially sort of rotational motion, right? So it's going to be radius times omega dot, which in this case would be theta dot. So this would be a half m a squared theta dot squared, okay? Where v is basically a theta dot. I'm not going to deal with the Lagrangian here because I don't really need it. What I'm interested in is total energy, right? So the total energy, E, is T plus V in this case. And so this will be a half m a squared theta dot squared minus m g a cos theta. Okay, so we can draw an energy diagram for this, and I know I was just talking about velocity phase spaces, but I'm going to want to set this up by looking at the energy diagram first so I can understand where the behaviors are coming from, and then I'll show you the velocity phase space diagram. The velocity phase space diagram will make a hell of a lot more sense if we've done it. So we don't need to do this, but it's helpful for the argument. So what I'm going to do here is plot on my x-axis my positional coordinate theta, and then I'm going to draw it in the center just to keep things simple. I'm going to have on my y direction, I'm going to plot potential energy in this particular case. Now, if we look at our potential energy term up above, it's minus mga cos theta. And in a second, you'll see why that minus sign is there from a physical perspective. Okay, so if we consider 0, that's going to be the position down here. And this would be minus mga, right? Because cos of 0 is 1, and we end up with minus mga. Then you'll come out of here with a cos dependence. So hard to draw in symmetry, so you can work this out later, but this is mirror symmetric about 0, even though I can't draw it so well. pi on 2 on this side, and this would be minus pi on 2 on the other side. And that would be the point where we cross through 0, where cos of theta is equal to 0 at pi and pi on 2. And then we would go up and reach our maximum up here, like so. And this will be at position pi and minus pi. And then, of course, this is corresponding to cos of minus 1, okay? And then, so the point up here is MGA. And then we would come down on these other two sides in here. And I'm not going to draw any more because you know it's symmetric and continues going out. It's quite well behaved. Okay, so we can think about two particular positions in here, right? The first one to think about is theta equals 0. And theta equals 0, of course, is this position down in the bottom. And what it corresponds to is basically my pendulum hanging like this, right? And what you know about the physics down there is that if you take your pendulum and displace it very slightly to one side and let it go, it will return back to that original position, right? There's a force acting back towards the equilibrium point, and it doesn't matter which side I take it out to, it will rotate back to that equilibrium position. We know that that comes about in potentials that have minima, right? And so you can see this makes sense in here that this is minus mga cos theta in here, because if you now consider this position in the bottom here, we take some displacement out to here and let go of the particle, it will return back to there because you've got this minus, f equals minus dv on dx term. The slope is pointing in this direction, like this in here, so the force will act back to the center and you'll push your system back to equilibrium, okay? So this will give you oscillatory motion. And it's a position that we call stable equilibrium, right? Which means the particle's not moving, it's at equilibrium, and if we give it a push, it returns back to its equilibrium point, okay? Now there's another 2 points that are interesting to consider here, which is our positions theta equals plus and minus pi. And those two positions are the ones up on top of this curve. And if you think about what that means physically, that's theta equals 0. This would be theta equals pi. It's a stable equilibrium position. If you hold the pencil in your fingertips yourself, you'll find that you can kind of get it to balance there reasonably well. But the one thing that you know is that if you give this a little kick, it doesn't come back to that equilibrium position. What happens is it falls out and heads ideally to the other stable equilibrium. So let's just try this and hope I don't drop it. Like so, right? And so you can see that in the graph here as well. The motion can fall to either side on here, and what it will do is find its way down into the nearest stable equilibrium position. So here what we get is directed motion towards the minimum potential, okay? And this is a position that we call unstable equilibrium. For now, we're just going to deal with those two, but I'll point out that it's not exclusively just those two. So you could imagine a potential, for example, that comes up like this and then goes flat for a bit and then goes up like this. And then this equilibrium here depends on which direction you push it, right? If you push it in this direction, it's a stable equilibrium. If you push it in that direction, it's an unstable equilibrium. And you can end up with all sorts of interesting equilibrium points as you go further and further along in dynamical systems, okay? But we'll keep it to those two for now. Okay. What happens in our system here then also depends on what our total energy is. And we can draw 3 different scenarios for our total energy. We can draw one that's down here somewhere, and we'll call it EA. We can draw one up here that we call EC, and we'll deal with it second. And you can draw one that very precisely here goes through the top of that curve and through the top of that curve, and we'll call this one EB. Okay, so let's work our way through and look at these 3 cases real quick because these will really set us up for this velocity phase diagram. So if you consider EA, let's go through it really quickly. You all know this one from first year very much so. You basically get your motion moves up to the point here where the potential energy is equal to the total energy, the kinetic energy is therefore zero, the particle stops, and then the potential will drive it back down. And so what you would basically get here is a swinging oscillatory motion to the 2 points as you work your way through. Okay, the higher EA is, the bigger that displacement gets. Okay, so if EA is right down near the bottom here somewhere, then you've got a very small displacement. If EA is right up where it is there, it's almost getting up to the pi position as it moves through that motion. Okay, so EA basically just corresponds to simple oscillatory motion. It's not very difficult. Let's deal with EC for a second. EC, if you think about it, the system has heaps of energy. It's like coming in here and just karate chopping this thing around. And it will go up through the top of the system. You'll notice when you get up to this top position here, the kinetic energy is not yet zero because the potential energy is not equal to EC. So there's still kinetic energy coming through the top here. And so the system will go back into the next part here and then keep going round and round and round, okay? And so you can imagine being up in this space up here and basically going continuously this way from one rotation to the next rotation to the next rotation. And each of these could have its own little oscillation in the bottom of it, okay? So this is rotation. And then we have our position EB, and EB is kind of a knife's edge. It's what in physics we tend to call a separatrix. It's a line dividing two separate pieces of behavior, and usually in such a case that even just epsilon off to the side of that line, you're in one type of behavior, and epsilon off to the other side of that line, you're in the other type of behavior. It's really like a razor's edge. And the example I usually like to use for this is if you've ever been to a theme park, they often have these pirate ship rides. So you have these two struts coming down from a pivot point at the top. You have the ship, people sit in the ship, it goes like this, 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 and then eventually it goes all the way over. And usually they have some fun when they're slowing it down. You slow it down just to the point where it comes almost up to the top and it sort of sits there and hangs and has to make this decision of does it fall over this side or does it fall back this side, right? And if you think about this for a second, you come up into this top position and now you're in this unstable equilibrium. And if you fall that way, you kick off the rotational motion because you keep accumulating more theta. Or if you fall back the other way, you go into this oscillatory motion, right? And this is this really fine divide between the two. And we often used to joke as kids, it would be kind of amusing if you could get it to stick in some position where it's just stuck at the top and it never tends to fall down either side. And it's actually really hard to get a ride like that to do that without some active brake, because the smallest perturbation to this unstable equilibrium, it could even be someone on the boat just waving their arms around, will make it decide to kick one way or the other, okay? So this EB here is a thing we call the separatrix. Okay, so I'm not going to draw it on my iPad because it's going to take me forever and I'm not going to draw it anywhere near as good as I've got it in my notes. So I'm just going to skip directly to it in my notes. So here it is, a velocity phase space. So what we're plotting here along this axis now is theta. Along this axis here is theta dot. And you can see this is broken up into some separate regions. There's these regions in here that have got these circles in them. And then there's these regions on the top that have got these wavy bits in them. And then there's this line shape in here in the middle that is kind of the divider between the two. Okay, so let's talk our way around this. This circle in here, let's follow one of these circles. So we would start here, which would be theta equals 0 with some velocity, okay? And so you can imagine we're coming through here with some velocity. We come around to some point, which is here, where our angle is finite, but our theta dot is 0, so it's stationary, right? So that's the end point of the motion. then we come to here, which would be coming back through the center with some velocity now in the opposite direction. We come to here, which is stopped on the other side of the motion, come to here, and then that's back to the beginning. So this is just oscillations, right? And as you can see, each of these circles moving successively outwards is just bigger and bigger oscillations all the way through, okay? And you can imagine when you get right up against this line here, that basically corresponds to you oscillating almost to the top, and then almost to the top, and then almost to the top, and then so forth, right? If you now jump out into this position here, you've now got enough energy to go all the way around over the top. And so you can imagine starting over here somewhere where you're just before you come to the top. This would be now get to the top, you're minus 2 pi. You now come through the bottom and back out to the top. This would be the top just here. Sorry, got this wrong. So this would be bottom in here. This comes through to, sorry, this is the top just here. And then your maximum velocity will always be at the bottom. Okay, so this is where you come through your 2 pi position at the bottom. Come through here to where pi is, so that's back at the top. Then you come through this position here. This is the obvious one now, you're back at your 0. You go through here, so this is another rotation coming through here to the top, to the bottom, and so forth. So if you move along this line, just in case in the last demonstration I kept changing the direction because it's hard to keep track of, this would basically correspond to from minus 2 pi to minus pi to 0 to pi to 2 pi to 3 pi to 4 pi and so forth, right? And so rotating in one direction is in this top set, rotating in the opposite direction is in the bottom set. And you can imagine as you lose energy, you get to this separatrix where it's basically the point where you would stop at the top here, okay? Now, the interesting thing is the periodicity in this plot. So if you imagine starting at the 0 point here, which would be this, and imagine what we do is we give our system a little bit of energy, so we sit up on this circle out here. So this would correspond to doing this sort of motion, right? And what we're going to do is give our system a little bit of extra energy for a very short period of time, and then take it away again. So imagine that we're coming up into the top of this motion, and now we pop up to here. So we get a little bit more energy. And what happens is we now kick it over the top and come into this part of the system. And then we drop back into this circle and come back into this oscillation. Now we've accumulated like an extra 2 pi of phase in this system, right? And it's still the same type of motion. Whether we do it here, or we go back round one and do it here, or we go back round one and do it here, this behavior that you see in the bottom is the same in each case. It's a periodic system. And so that's why you see these repeated as you go through this system, okay? So this is sort of your first example of a velocity phase space. And the one thing you'll notice if you draw one of these is that, this separatrix line here is a point in the graph where you almost can never reach, because you're either going to find yourself a little bit on one side or a little bit on the other side, either in a solitary motion or in rotational, unidirectional rotational motion. And you can kind of understand that behavior from these sorts of velocity phase spaces. One place where you see a lot of these is if you go on to do chaotic dynamics, where these sorts of phase spaces become very interesting and have some really interesting sort of pattern properties in terms of fractal structures and those sorts of things. And if we have time, a spare half a lecture near the end of my half, I might talk just a little bit about that in this part of the course. Okay, so I'm going to stop here for a moment, keep this lecture, this half of the lecture kind of short. And what I'm going to do in the second half is basically go through and derive all of the equations that come about for single harmonic motion and go from there, and keep this first bit sort of self-contained piece on velocity phase space. So let's just take a short break here.